Yeah, I can see it.
My name is Dylan Buckner.
Hold on, pause. My name is Jaden Benton,
I'm Dylan Buckner, if you didn't get that.
and I'm
And
Jaden
our
Benton.
project is named Sorting. To start off with, we're going to talk about the merge sort algorithm. It's a classic divide and conquer algorithm that is used to sort an array or list of elements. And it starts off with dividing the array into like two halves, and then you do this over and over until there's a subarray that contains just a single element, and then you combine them back together in a sorted way until it's from like a smallest to largest element, and you do that until it's an entire array again. As seen here, you got the whole, and you divide, 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 then you combine again, and then you combine one final time to get this whole entire array. Characteristics is the time complexity, which is O parentheses n log n, and in all cases, because it consistently divides the array into two halves and merges them. The space complexity, O parentheses n, because it requires additional space to hold the divided arrays. Stability. Merge sort is stable, meaning that it preserves the relative order of equal elements. Parallelizability. Merge sort is well suited for parallel processing because of the divide and conquer approach, which can easily divide among the multiple processors. Here is the output picture of our data text file using the code for our project. As you can see, it does 520 milliseconds to execute the actual sorting, although it takes a lot longer to actually display it. Next, we have the counting sort algorithm. It's an integer-based one that works effectively when the range of inputs is known and is not significantly longer than the number of elements to be stored. It operates by determining the position of each element in the stored array, using the count of occurrences of each unique element. As you can see, these are the steps: finding the range, creating and populate the count array, modify the count array, build the output, and copy the output to input array. And that's only if it's needed. I'm not going to go deep into this. Here's a picture of the count sort array in a table form. The characteristics, it's O parentheses n plus k, where the n is the number of elements and k is the range of input values. It's the same for the space complexity, as it requires additional space for the count and output arrays. It's stable, meaning that it preserves the relative order of equal elements. And its limits is that it's only effective when the range of inputs, which is k, is not significantly larger than the number of elements, which is n. And here we have, once again, the output for the count sort algorithm. As you can see, it's 630 milliseconds or 0.63 seconds. It is rather the fastest one that we had for this code. And Jaden will continue for the next part.
All right, so now we have the third algorithm, which is quicksort. Quicksort is a highly efficiency sorting algorithm that uses the divide and conquer strategy as well. It works by selecting a pivot element from the array and partitioning the other elements into two subarrays according to whether they are less than or greater than the pivot. The subarrays are then sorted recursively. And here's a step-by-step explanation of the process. You choose a pivot, partition the array, and recursively apply quicksort. And this is an example that we have provided about how quicksort goes. So you have 13 right here, then 13 comes right here in the middle, and then you have 13 right here at the top, then 13 right here. And then you see at the end, 11 and 16 is highlighted, and then they go in the middle on the row under them. And then you have 11 at the top, 11 right here at the top, and then you have 16 right here and 16 right here. And then you see at the end, you have 4 and 11. I mean, you have 4 highlighted right here, and then you have 18 highlighted right here. And then they go at the bottom. Then you have 4 right here and 18 right here. Characteristics, time complexity. Best and average case, we have O parentheses n log n, where n is the number of elements. Worst case, we have O parentheses n squared, which occurs when the smallest of large element is always chosen as the pivot. Space complexity, O parentheses log n for the best and average case due to the recursion stack. O parentheses n in the worst case of the recursion stack if the pivot divides the array in a highly unbalanced manner. In-place quicksort is an in-place sort. It doesn't require any extra storage proportional to the input size. Not stable quicksort is not stable sort. It's not a stable sort, excuse me, meaning it does not necessarily preserve the relative order of equal elements. And here's our when we ran our code, we have our output right here and using the data text file. And as you can see, that quicksort was one of the quickest times and it came in at 500 milliseconds showing the output of the code. The fourth algorithm that we have is insertion sort. Insertion sort is a simple and intuitive, comparison-based sorting algorithm. It builds the final sorter array one element at a time. It's much like sorting playing cards in your hands. You take one card at a time and insert it into its correct position among the already sorted cards. And here's a step-by-step process of how insertion sort works. Start from the second element, compare and insert, and repeat. And right here we have a picture, an example of how it would look if it was in a chart. And we have, so like basically you start with the second element as a key, then you go right here, you switch 5 and 1, so then you make 1 become the second element. It's like you just keep repeating as you go down and stuff. The characteristics, time complexity, base case, parentheses n occurs when the array is already sorted. In this case, insertion sort performs only n1 comparisons and 0 swaps. Worst case, 0 parentheses n squared occurs when the array is in a reverse sorted order. In this case, for each element, insertion sort may need to compare it with every element in the sorted position of the array. Average case, O parentheses n squared. Even though a insertion sort may perform fewer operations on partially sorted arrays, its average case time complexity remains quadratic. Space complexity, O1. Insertion sort sorts the array into place, meaning it doesn't require any, and I mean any, additional space proportional to the size of the input array. It only uses a custom amount of extra space for temporary variables. And here's the output when we use the data text file of insertion sort. And as you can see, insertion sort was also quick and it came in at 500 milliseconds, showing the output of the code.
Okay, so to finish it off, we have a little ranking here. Quick sort is number one, then merge sort is two, counting sort is three, and insertion sort is four. Now, I know this differs with how the execution times are, but this is a gigantic amount of code. So even though quicksort and insertion sort are the same numbers, quicksort is a lot faster and a lot more efficient when performing this. So on the average, when it's just a normal amount of code, it is usually faster. But when dealing with a large amount of code like this, counting sort is the more efficient way to go. But overall, quicksort is one of the more faster ways. And that should end our presentation. Thank
Thanks for listening, guys.